It's my pleasure to introduce Dominik Hangleiter, who will be talking to us about precisely identifying Hamiltonians.
Awesome. Yeah, thank you so much for having me. It's been a great workshop so far. Right, so today I'll tell you a little bit about some work I've been doing together with Ingo, Jens, and Pedron on identifying Hamiltonians from data, from dynamical data. So what's the task? In physics, we care about nature, right? In particular, we are quantum physicists, right? So we care about quantum nature. So physics at the level of, say molecules or so. And of course, we all know since our, first year in physics that the basic object in quantum mechanics is the Hamiltonian. That's the object which describes all of, the static and the dynamical properties of quantum systems. Right, so in the last couple of decades, we've had this amazing progress in laboratories all around the world in terms of controlling quantum systems, in terms of actually designing Hamiltonians in the lab. So here's a picture from Emanuel Bloch's lab in Munich, where they have these cold atom quantum simulators, and they've been doing an amazing job at really, tuning like the individual parameters of the Hamiltonian. But of course, in these systems, we can tune the interactions really, really well. But on the other hand, we also, need to know what's actually the Hamiltonian in the lab. So, we need that both in terms of engineering, right? So we have some control model of our system in the laboratory, and we want to update that control model to really get more and more precise in terms of engineering the Hamiltonian. But then on the other hand, of course, we're also doing something, and we want to know, is what we're doing the right thing? So Hamiltonian identification is a task that on the one hand we can do, right? Because we are able to actually engineer Hamiltonians, which are very simple. So we can sort of break it down to like a very, simple instance of Hamiltonian identification rather than trying to identify the Hamiltonian immediately of chlorophyll or so. But on the other hand, for these analog quantum simulators, it's also something that we really need when we really want to make them precise and in the end use them as computational devices. Okay. So today I'm going to talk about Hamiltonian identification for a specific class of systems, namely Bose-Hubbard systems, precisely the kind of system that Emanuel Bloch and other people have in their labs. So the Bose-Hubbard Hamiltonian is a very simple Hamiltonian. It's just a hopping term with some parameters and an interaction term and a local potential. Right, and this Hamiltonian, I have to say, it describes cold atoms and optical lattices, say, but also superconducting qubits. It's a very generic model. So today we'll be looking at specific experimental systems also, specifically superconducting qubits. And even more specifically, the superconducting qubit chip that they have in the Google AI quantum team. And we're going to make our lives easy. We're just going to look at the non-interacting part of this Bose-Hubbard Hamiltonian. Hamiltonian identification is a difficult task. So, for us, we try to make the task as easy as possible and then, start building from there. Okay, so that's the goal for today. Given dynamical data from, hopefully this Bose-Hubbard Hamiltonian, identify the parameters of this Hamiltonian. So the Jij and the μi. And I'm going to show you an experiment how we actually do this in superconducting qubits. Right. I should also say, please interrupt me at any time with questions. Please. Okay. Good. So let's start in theory land. In theory land, people have thought about Hamiltonian identification, of course. And there's like various proposals for how you can identify Hamiltonian. And there's basically two settings. One is the static setting. In that setting, people have looked at identifying Hamiltonians from eigenstates or identifying Hamiltonians from thermal states. And there's this very nice result by Anurag Anshu and others who have shown that a Hamiltonian, a local Hamiltonian, can actually be identified from polynomially many measurements on a thermal state of that Hamiltonian. So that's nice, but yes.
And these measurements are local?
These measurements are local, yes. So that's just Pauli measurements. Right, but okay, we know that preparing thermal states isn't really something that we can do very well on analog quantum simulators. But on the other hand, there's these proposals looking at dynamics actually. So most notably, a recent proposal by Lee and others, the group of Timothy Xie, who look at generalized conservation of energy. And this is a very nice proposal, which actually sort of developed parallelly to our work, I guess, although we were much later at actually writing a paper. And I think this also would work in practice. It's not what we have done, but I think it will also work in practice. And it's an interesting question to look how it actually compares in terms of resource requirements, which Hamiltonians we actually get from these different methods. And then there's a really nice method by you and others who show, this is again more a theory work, that if I look at short time dynamics, so just up to second order Taylor expansion, then we can actually identify Pauli sparse Hamiltonians. So this is much more general than local Hamiltonians, right? Just Hamiltonians which are sparse in the Pauli basis in a span robust way. This is amazing. So I'm going to talk about span errors in some more detail later, and hopefully you're going to be able to appreciate why this is a great result. Although I have to say, I don't think that this is actually a result that we would use in practice. So this, uses randomized benchmarking as a subroutine. Like it's a very intricate protocol. Okay, so this is theory. On the other hand, there's like a very small scale experiments, mostly in NMR systems up to 3 qubits or so. And there's this method by Zhang and Zarawa, which is actually in spirit quite similar to what we do. Although I think it's in the end not going to be as robust to the kinds of errors that we actually see in dynamical systems. So in these NMR experiments, the dominant source of error is decoherence. And this contrasts with what we actually see in this superconducting qubit processor in the end. And then there's also very nice work by Samak and others who've done Liouvillean tomography. So they basically try to do nothing for some time and then see, what are the sources of errors in their system. Markovian errors. Right. Okay, so basically our project started with Pedram coming up to us and saying, we have all these works, but how do we actually do this in the lab? How do we identify our Hamiltonian? And the challenges that they're facing, or that we've been facing, is that there's a lot of, of errors actually in the system. So we have incoherent errors, but also state preparation and measurement errors, which really screw up your dynamics, as we found out. Then we should be able to scale it up to intermediate sized devices, say tens of qubits or so. And it should be something that, I can't only prove that I can scale it up, I should be actually able to do it. Right, so our goal for this project is we just want to come up with a scheme that works on these kinds of data that we can take on these signal processes. All right, so okay, let's zoom out again. What's the task of Hamiltonian identification? Our scheme is very simple, so I'm going to try to walk you through every step as much as I can. All right, so the task is we have dynamical data. Right? So we have some input states, psi n. We evolve under our Hamiltonian, then we measure some observable. I guess you could generalize this to measuring in a basis. We're just looking at measurements of observables. Okay, so the immediate questions that we're facing is, okay, what kind of input states and what kind of observables are required in order to actually pin down the Hamiltonian? And then, a closely interlinked question is, how can we actually identify the Hamiltonian from those data? So these are questions we should sort of look at in parallel, right? Of course, I know that I can just, prepare like a full basis of Hilbert space, measure a full operator basis. That's going to pin my Hamiltonian. But this is not something I want to do. I want to do something where I can actually have an efficient post-processing algorithm that are run on the data in order to recover the Hamiltonian. Questions so far? Oh, excellent. Okay, so what are the challenges? The challenges are that, well, just looking at this data form, naively, you just need, full simulation of the time evolution. And if I do that in Hilbert space, that's something I don't want to do. And on the other hand, you see the Hamiltonian up in the exponential, so it's a highly nonlinear reconstruction problem. Like in contrast to say state tomography or process tomography, which is just a linear reconstruction. So these are the two main challenges that we're facing. Okay, so we are going to solve the second challenge first. Well, the simulation challenge by just defining our problem, namely by just looking at non-interacting Hamiltonians. Okay, non-interacting Hamiltonians, are Hamiltonians that if I just look at, say, the single particle sector, so this is the particle number conserving Hamiltonian, right? So I can restrict to particle sectors in Fock space. If I just look at the single particle sector, this is just an n times n matrix, right? And this is actually what we're going to exploit. So we look at the Hamiltonian H, which is just hopping an on-site term with coefficients Hij. The task is identify Hij. Okay, so what are the kind of data and the initial states that we're using? The kind of data that we're using is time evolution of this annihilation operator in mode M. Okay, then you can see, convince yourself that this is going to be linear in this matrix e to the minus ith, where now h is the coefficient matrix of the Hamiltonian above, right? So this is going to be an n times n matrix. And it's nice, right? Because we've, usually you'd have conjugation, right? So quadratic problem, e to the minus ith. With these data, we actually have a linear problem. That reduces our complexity further. Yes, please.
Here you're already assuming a form for the Hamiltonian.
Yes.
So what you're trying to find is Hij.
Yes.
Okay, so is this more like a parameter estimation or is it Hamiltonian?
Well,
They're the same.
yeah, in my languages, that's the same, right? Because in the Hamiltonian reconstruction, I want to start with a model, and then I want to identify the parameters of that model. And that, I think, you do very generically, right? Even if your model is, I have a 2n by 2n, 2 to the power of n by 2 to the power of n matrix. Right, so here we have a model with order n squared many parameters. Good. Okay, so this is the observable which we're going to measure. The initial state which we're going to prepare is a superposition between the zero particle sector, so just zero, and then one excitation in one of the modes. So this is what I denote by this 1n vector. Okay, this is nice, as you're going to see in a moment, because that basically means that I can decompose the Hamiltonian into something which directly has the, the eigenfrequencies in the exponential, as opposed to differences between eigenfrequencies, which you usually have for arbitrary initial states. Right. So now you can convince yourself that if I look at, what's actually the measurement data now, this is just going to be matrix entries of this e to the minus ith, h the coefficient matrix. So now we have data which just, give us a unitary matrix with this orthogonal matrix actually, because we're just considering real parameters, with just this h in the exponent. Okay, so now the task is from those data recover h. This, yes, please.
Is the model boson and you're mapping to qubits or?
Well, yeah, okay. So superconducting qubits natively are bosons, and then they're using them as qubits essentially. But yeah, I mean, we're mapping to qubits. Like all we're doing is in the one particle sector, right? So it's just qubits, bosons, fermions. It doesn't make any difference.
So the phenomenon you want to simulate are give two levels.
Well, I mean, depends on your perspective. Yeah, I mean, you can also write these Hamiltonians in terms of sigma x and y if you want. Because because we're just looking at the one particle sector, and there I can, just put one excitation. But we are phrasing this in the language of bosonic systems. Yeah.
You still do coherent space and protocol would work fine, I guess.
I haven't considered that, but I guess you could, yeah. Does that answer your question? Or? No? Okay. So the mapping to qubits is very simple, right? You just identify the position operator with x and the momentum operator with y, and then okay, good. Okay, and now the key is, of course, as I already reiterated, this is an n times n matrix, so this is linear and this is size. That's what's giving us scalability. Okay, now you could ask yourself, how are you going to measure this annihilation operator? And then I can only measure emission operators. Well, you just decompose it and then combine the data. Great. Yes.
It seems here that when you're actually extracting, it's like mod sum 2 pi, like because it's in the phase of being defined strategy. So you're not really extracting H, you're extracting it mod 2 pi or mod 2 pi or T or whatever. Like that matter to you, like in the parameter, like a true parameter estimate would probably be more efficient than the actual value of H. So you have to do more tricks to like account for the space wrapping stuff.
I don't think you do.
P can be any real number.
Yeah. Right, so, okay, let me continue for a moment and then maybe the question solves itself. Okay. It's still wrong. Oh, sorry. Okay, right. So the kind of data we're taking is, right, we prepare an initial state depending on the mode, and we measure an observable depending on the mode. So we have n squared data series now as a function of time, right, where we prepare what's the n is initial state, right? We prepare qubit 1 in half an excitation, we prepare qubit 2 in half an excitation, and then we measure qubit 1, qubit 2, qubit 3. Mode 1, 2, 3. Into switching between qubit and boson world. Okay, this is the kind of data we're taking. And the way we're thinking about this data is as matrix value time series data. So at every point in time, right, we said we have e to the minus ith with h the coefficient matrix. At every point in time, I have a matrix. So we think of this as, you know, having a matrix at t0, t1, and so on. Right. So now how are we going to reconstruct the Hamiltonian? The key idea is, again, something we learned in undergraduate course. We do eigendecomposition of that. Right. This is nice because it separates the nonlinear part of the reconstruction into something which is scalar, essentially. And then we have the linear part of the reconstruction, which is just finding the eigenbases of it. Good. And, you know, with this, we know how to, you know, do Fourier transforms and actually extract frequencies from data. And then, once we have those frequencies, we can go and reconstruct the eigenvectors. Okay, good. Right, so when extracting the frequencies, we have to be extremely careful, right? Because this is in the exponent. So we have to be extremely precise. So a normal Fourier transform is limited by the Nyquist frequency, right? If I just do discrete Fourier transformation, I know that my frequency resolution just scales as 1 over the total evolution time. And that, you know, if I don't want to go to infinite time, is a very limiting factor. So we have to do something more clever. And what we're doing is actually we're inspired by mobile communication setups, where, you know, the task is you have like, I don't know, some radio wave signal coming in from like various directions, and now you want to reconstruct the angles from which these sources come. And people in this setting have developed an algorithm called ESPRIT, which is super resolving and denoising. And I'm going to explain to you in a second what that means. Yes, let me first explain the algorithm, and then I explain in what sense it's super resolving and denoising. Right, so the algorithm takes as an input data, which is just an equally spaced time point. And then what we do, right, we have matrix value data. The algorithm as we're using it at the moment is just a scalar algorithm. So we have to compress our matrix value data for the purpose of applying this algorithm to a scalar. And the way we're doing this is by just taking the trace. And this is nice because it just gives us a superposition of all the frequency components with equal Fourier coefficients. Right? If I look at, like, say, one matrix entry of this matrix entry of this time evolution matrix up here, then, you know, the Fourier coefficient could be very different, and I could, you know, see different components with very different strength. And indeed, like, some of the components could even be swamped by noise or not existing at all. So by doing this, we ensure that we see all the Fourier comments. Yeah.
Where does the data come in? I think I missed that.
This is the data. Now I take the trace of the data.
Oh.
Right, so at every time point I take the trace. That gives me now linear data.
So the lambdas are the things you want to estimate.
Exactly.
Right? And you're evaluating this S of L.
Yes.
But that doesn't seem to depend on the data at all. It only cares about times you measure at and the things you want to do.
No, think of S of L as our data. So the way we construct S of L is for every time point, we have this e to the minus ith.
Yeah.
That's our data matrix. Right?
Okay, yeah.
And then I take the trace of that data matrix. That's S of L.
And
at
send that
point
L to the e to the minus side to connect them.
Exactly.
Okay.
In the ideal setting, right?
Right.
Now, if I add noise, you know, there's things happen, right? Like additive multiplication.
Okay.
Okay. And then the algorithm, I'm not going to go through in detail. I just want to show you it's a very simple algorithm. I just take, you know, construct a matrix from that data. And, you know, I do some SVD, and in the end, I calculate eigenvectors, and that's going to give me the frequency. So it's a very, simple algorithm that takes like 3 lines of code. Okay, so now this algorithm is super resolving in the following sense. Now look at these, I don't know what the color is, like greenish points. That's just the discrete Fourier transform of our signal. And the blue lines is essentially the signal that this ESPRIT algorithm sees. So we're taking an SVD somewhere in the middle of the algorithm that essentially denoises the signal. So you can think of like the large singular values as actually your signal space, and then everything else is just cut out. So this algorithm sees like a highly super resolved signal in a way that maybe you could construct from this discrete Fourier transform, but it's not. Okay, there's actually some theory about it with respect to how precise you're actually going to get using this algorithm. And basically, this depends on the noise. So this eta is just the additive noise I showed you before. And this should be smaller than something which is called the super resolution factor, which essentially depends on the minimum frequency distance you have in your data and the number of, the length of the time series. Now, this is some theories result. The nice thing is it's just linear in the noise. And in practice, we find that you get like up to 4 times more accurate than like this frequency in the presence of noise, which is so nice. Okay, so now we have the frequencies. Now we're going to input those into the eigenvector reconstruction. And the way we do this is we just solve the least squared fit problem in a clever way. So what's the least squared fit problem? We just have the data and we subtract from this e to the minus it. Now we input our found frequencies, and the task is find the O that minimizes this expression if I just take the L2 norm of the entire data. Okay, the way we do this is by a clever non-convex optimization algorithm, which just essentially exploits the structure of the orthogonal unitary group. And we find like a nice 1 over square root of number of data points scaling. And we tried this here for different algorithm, and it turns out that in the setting that we're at, in this naive setting that we're at, you can actually also just do linear inversion, because we're just in the, we're not in the setting where we have sparse data, like we're not constrained by the amount of data that we have. So it actually also works with linear inversion, but there's other reasons that I might not get into now, why we want to do something. Okay, now let's get to the maybe more exciting part of the talk, namely the experiment. So what's the experiment? We use the sycamore chip. Of course, all of you have seen this picture. And so what's the layout? You have these qubits and couplers arranged in this like square grid. And we're going to use not all of the qubits at once, but just subsets of these qubits. And we're usually going to arrange them in a linear chain, although that just happens. But our algorithm requires that. Right, so how do they do the experiment? The way they do it, they have these tunable couplers, which they tune the frequencies of those couplers in order to switch on the interaction. So the way they do these analog experiments on the Sycamore chip is they have their qubits and couplers at like native frequencies at which they don't see each other. They do all the single qubit gates there. So state preparation, right here I'm going to do a pi over 2 pulse to prepare the first qubit. Then I ramp the frequencies of the qubits and couplers so that they come, around the common frequencies around which they're detuned. That's going to switch on the interaction. So then I let it run. For some time, I'm going to tune the frequencies back, and then I do my measurement. Okay, that's how they do it in the experiment. The way we look at this as theorists is I have some, ramp phase that's going to give me an initial map in the time evolution. Then I have the ideal Hamiltonian time evolution, and then I have some measurement map. So the kind of data, right, in this ideal setting, I said we just have e to the minus ith. Now this is modified to s e to the minus ithm, where s and m are just some linear maps. Okay, this is bad, right, because s and m just wildly rotate the bases. Okay, now the first observation though is, forget about the measurement error, just consider the initial map. You can just get rid of this by taking the inverse of your data at a fixed time point, right? Because we assume that S is the same for all time points. We can just take a fixed time point, take the inverse, multiply it from the right to the data. That's just going to give us data which is shifted by some t, which is precisely the t at which I took the inverse. Okay, now you might worry that this this gets rid of our measurement map in the ideal setting. Now you might worry that this is very sensitive to noise, right? Because you're taking the inverse, that's usually very sensitive to noise. So what we're doing is we're just averaging over many such data by concatenating them for, if we do that for different times. And this turns out to work really nice. The nice thing is now we can actually also get an estimate of this initial map by just again multiplying from the left with our recovered Hamiltonian in ESPRIT.
Yeah, so when you say it works nicely, do you mean based on like simulating data and testing it, or a long process? More about
Yeah. So okay. So it works really nicely in simulations. So essentially, yeah, in simulations when we just what direction am I going? Yeah. Yeah, so in simulations, when we just add a random initial map, just a random linear map, and shock noise or so on, then this essentially recovers the data just as well as if there hadn't been. And then in experiments, we see that if we don't do that, we just get a mess. If we do that, it looks nice. Yeah. So this is essentially how we got to this model, right? We just get a mess, and then we started talking about the pattern. Well, it might be something that's happening. Yes?
Previously, you were talking about non-interacting Hamiltonians.
Yes.
Is it still the case?
Yes. Everything I do is non-interacting.
Because like you were ramping up the queue.
Exactly, yes. So, okay, I switch on the hopping, right? So before I ramp the frequencies, there's no hopping between different sites. Now I ramp the frequencies, I have to ramp up the coupler so that there is hopping between different sites. Yes, that's right. Great. Okay, so now we have the initial map. Now you see there's a symmetry here, right? If I had a final map, so a measurement error, instead of an initial map, I could just do the same thing by multiplying from the left and then get the final map by multiplying from the right. But, so you might wonder what's actually better. So this is the first data that you're going to see. We looked at this in the data and we found that it's better to remove the initial map if you want to improve the recovery of the Hamiltonian in the sense that the Hamiltonian that we recover is closer to the Hamiltonian that pattern expects that he has. And it's also better in terms of actually fitting the data. Okay. Good. Right, now there's not only an initial map, there's also a measurement error. So this is a problem, right? So what happens with the measurement error is, now, right, if I take the inverse, I just rotate my data by this measurement map. So I just rotate the data into different places. And in some sense, this is also inevitable, right? I'm just going to look at my quantum system through the measurement. So if the measurement is faulty, there's just no way of knowing, what is everything okay? Yeah. There's just no way of distinguishing that from just a Hamiltonian which has a rotated eigenbase. In the absence of additional, calibration, of additional assumptions on the Hamiltonian. Okay, but there are some observations which are good to know. So the first observation is that the frequencies are unaltered, right? I just rotate the basis. The frequencies remain the same. The second observation is that the eigenbasis of the Hamiltonian in our algorithm is actually constrained to being orthogonal. So I said we use this non-convex optimization algorithm, gradient descent-based algorithm. In that algorithm, we just constrain the basis to be orthogonal. So actually what we're going to see in the algorithm is just the orthogonal projection of the measurement error. This is already much better because it constrains us further. Now, finally, there's another observation, namely that if you, so based on the previous, if the final measurement error is just a diagonal matrix, so just has phases on the diagonal. So this is something that arises, go back to this model here, that arises in the setting in which you just ramp the diagonal increase, so just the qubit frequency, yeah. So just the qubit frequencies and not the couplers, right? So the couplers, if I ramp those, that's going to rotate my measurement error to an off-diagonal. Whereas if I just have the diagonal, which I ramp, then I just give it the diagonal measurement. Okay, and this is approximately what's happening. It's not precisely what's happening, but approximately what's happening. Okay, and in this case, if I project to orthogonal, I'm just going to see plus minus 1. Okay, now we can make the assumption that Pedram doesn't mess up so badly that he, just gets the direction of his coupling from us. So, and, just identify the plus minus 1s in the eigenprojectors corresponding to what Pedram expects that he has implemented. Okay, so given that, I now alter my initial map by this diagonal matrix M and my recovered Hamiltonian by this diagonal matrix M, which I thought. Okay, good. Then let's look at some data. So this is a 5-qubit set of data, and you can just see the X part of the data and these greenish dots. And now the blue curve is the Hamiltonian fit. So you can see this works really nicely, maybe not so nicely in this row, and there might just be some model mismatch, say the measurement has a larger error or so. But in general, it works really nicely. So now we can look at this in Hamiltonian language. So we have some target Hamiltonian, so this is all measured in megahertz. On the off diagonal has a constant coupling of 20 megahertz, and then we have random fields on the diagonal. Okay, now we can look at what we identify, and you can see that roughly this is the same up to, so this is multiplied by 10, sort of errors on the order of 10% in the matrix entries of the Hamiltonian. Okay, and we can look at the initial map and the final map and see, there's actually something non-trivial happening in the measurement. And the initial map is, close to diagonal, but not really diagonal. Like, ideally, you'd want an identity in both. Okay. Yeah.
So they have this target Hamiltonian.
Yeah.
They must tune it up.
Yeah.
So then, so for example, like tuning to 1 and then measuring 0.1, you identifying 0.1, like what's the, sorry, in the third row, like what is, like, do you know what happened there? Was there calibration already not?
Yeah, no, so I think what happens is that this is just the measurement error. Like most of it is the measurement. I'm going to show you in the plot in the next slide, where you see that actually most of the error which is happening is the measurement error. There can still be like sort of reasonable error which is actually happening during the time evolution. But I always like to think of it as, if the measurement is wrong, then the Hamiltonian you implemented is also wrong, right? So previous to this project, Pedram also always looked at his data in terms of frequency, right? If you look at the data in terms of frequencies, it's beautiful. But right, if I want to measure actually, something non-trivial in the basis, then I actually see the Hamiltonian. So this is actually what describes your data. Okay, so now we can measure the quality of an implementation by just looking at the 2 norm and renormalizing by the number of qubits. And we can do the same for the frequencies. And in the ideal setting, those should be the same, right? If I get the eigenbasis completely correctly, those errors should be the same because the 2 norm is unitarily invariant. Right, now you can see they're not. So here on the bottom, there's the frequency error that we make. And on the top, there's the actual error in the Hamiltonian in the basis. These gray bars are our estimates of what the systematic error is, given on some guesses about the ramp speed and distance and everything. Right, so you can see that the frequencies are pretty good, right? So they're really sub-megahertz accurate, whereas the eigenbasis is like more on the order of megahertz, like five times worse or so. Okay, so now we can, further. So this is like, now we have many instances of a Hamiltonian for a fixed size. So this is 6-qubit data. So now we can, take the average. Now we can take our 5-qubit data, take the average of the frequencies. Oh, I've swapped the colors, unfortunately. Of the frequencies and the Hamiltonian. I can plot it. And I can plot the data fit error. So this is the right axis, and the Hamiltonian frequencies are the left axis. Okay, so this was data taken a year ago. Now we took some more data more recently on a different sycamore chip, and you can see the fit error is basically the same still. But now their Hamiltonian and frequency implementation quality are much worse. And that's just a matter of calibration. So now this new chip is just calibrated more badly. But you can also see, like we took data up to 14 qubits. Everything is pretty consistent, right? So doesn't make such a big difference whether they take 2 qubits or 14, 15 qubits. And in terms of the algorithm, we could easily proceed further to like 50 qubits. Yes.
Is the way that you define your error somehow rescaled with the number of qubits?
Yes. So this is the error per qubit, but like in a 2 norm. So it's not,
But this still means that if you increase the number of qubits, then the overall quality of the result will be worse.
Well, I guess it depends on your perspective, right? If I just look at, I don't know, measuring like a single qubit observable or so, I think, I don't know what would happen. Yeah, so this is sort of looking at matrix entries of the Hamiltonian, essentially. Like what's the error per matrix? Okay. Right, now we can also play other games. Now we can, rather than taking the average over many different realizations in terms of the total quality, we can also look at the median of the entry-wise quality. Okay, we can plot it like this, and so this is again our 6-qubit data set. And okay, this gives us a number for every matrix entry of the Hamiltonian in terms of the quality of that Hamiltonian. Now what we do is we choose that random subsets of the qubits and just implement Hamiltonian identification on those random subsets. And now we can, construct this map which sort of maps out the entire processor in terms of how well it performs analog dynamics. So we can really, look at the individual, ingredients of this chip and look at how well it's calibrated when we perform analog dynamics in median, right? This varies again a lot from data set to data set, but you can see that some components are much better than other components. And we can do that also for the initial map and the final map, which sort of tells us some really diagnostic data about the ramping and how this affects analog. Okay. So summary, how did we solve the problem? Well, the key, sort of take-home message is you use structure. So what structure did we use? We used sparsity of the frequency spectrum, right? This was used in this denoising algorithm, ESPRIT denoising algorithm. That's what allowed us to really get our frequency resolution much more precise than would be permitted by the Nyquist resolution alone. Use orthogonality of the eigenbases. Remember, that was important to really make the error that we get from the measurement much smaller. And also it gives us a really fast converging algorithm. Then we also, I haven't talked about that, we also use sparsity of the Hamiltonian support to really implement like a penalty term when you had like off-diagonal couplings which were farther away from anything that's physically reasonable or so. And we use removing of the state preparation error by, remember just taking the inverse of the time series. Now this is also, now the method is nice, right? Or using structure is nice because it gives you extreme robustness to noise. Right? Because all noise sources which don't respect the structure are just immediately cut out of our reconstruction. Right? In particular, all incoherent sources of noise don't respect the structure, right? Say particle or shot noise, diagonal phase noise is something that we actually actively corrected. Okay, so I wanted to spend the last few minutes actually talking about some, outlook things that we're working on. And one of those things is looking at two-body interactions, right? So we looked at just non-interacting Hamiltonian. We're also looking at two-body interactions now. And you can play the same game, right? Two-body interactions are, in the two-particle sector. So now you go to the two-particle sector, you prepare two excitations. And, this scales now quadratically or probably quartically in terms of the data in the number of qubits. So you might not want to do this for 20 qubits, but maybe you want to do it for 5 qubits. We haven't tested that yet, I should say, but this is how you would do it, right? You would now prepare initial states which have two particles, like which are superposition of the zero and the two-particle sector. Then you can, calculate what kind of data the analog, like what the time evolution of the analogous data is, and this is basically what happens in the single-particle sector plus what happens in the two-particle sector. So the protocol is, well, first run single-particle Hamiltonian identification, then run two-particle Hamiltonian identification. You're going to get this matrix just subtract h tensor 1 minus 1 tensor h, and you get an estimate of phi. I don't know how good that estimate is going to be, but in principle, this is something. Okay, now another thing is something that I'm looking at together with Michael and Noah and Ingo. Namely, Michael already talked to you about this nice solid state system. So we're looking at what you would do there, right? So there's like maybe different initial states that you can prepare, different measurements that you can make that alters your type of data, which gives additional challenges. And you might, the type of frequency reconstruction that we're using is not working anymore. So we need a reconstruction algorithm which actually uses the entire matrix as opposed to pinning it down to a trace data. And then now we're going to actually see frequency differences. So now we have to extract frequencies from frequency differences. And with Ingo and Jonas Spuckler, I didn't put their names here. We're now looking at actually vectorizing this ESPRIT algorithm, which is basically also what they did originally in this mobile communication setup, which is sort of quite naive. But but there's some challenges to be overcome here. And why would you want this? First, this is something that you want in terms of like when you actually want to scale up the system size to really make this algorithm scalable, right? Because if my frequency resolution scales as 1 over t, that's the same for the ESPRIT algorithm, right? Just scales as 1 over the length of the time series. But as I scale up my system size, I'm going to get more and more frequencies crowded in like my frequency window. So at some point, I'm just going to hit a limit. So you really want to have the frequency detection in such a way that you parallelly use all the data, right? You have enough data, so use it to actually get the frequencies accurately. Right, and then I already talked about data type. For some data types, you can't use the scalar version of the algorithm. Right, so now we want to look at actually the unitary with some coefficients in terms of a vectorized language. Right? We have these matrix entries of the unitary, consider them as a vector, and now like simultaneously put all that vector into the algorithm and give me. Right, what else? Okay, and then there's more theory questions to be answered, right? We could look at recovery guarantees for these variants of ESPRIT. Like for some variants of ESPRIT, we actually have recovery guarantees, but then also for the conjugate gradient method, to actually, prove that in the end, you're going to go this and that close to the target Hamiltonian. You can try and apply this to spin systems where, you just have some hopping and single excitations, which are outside of the Bose-Hubbard world of superconducting qubits. Then probably the biggest elephant in the room is how do you sort of get rid of measurement errors? And there's this paper that I mentioned at the beginning who like do RB of the measurements and then use short time evolution. This is theoretically nice, but yeah, I don't know how well this works in practice. And I wonder if this could also be adjusted to work with long time evolution or something. And then I also already mentioned how this compares to other methods, say on these generalized energy conservations. And there's more questions, so if you have any, let me know. Thanks so much.
Is Pedro or somebody else using this technique in their other experiments?
I think, okay, so Petram, I think, is moving away from doing analog things in general, which is why I'm not so interested. But I think they could. And this was actually initially the idea, right? The idea is automating calibration in like a, really data-driven way. You just, I give you my identification method, you run your identification algorithm at the beginning of the experiment, and then you can loop over calibration cycles. And of course, if you really want to do that seriously, you probably want to make it much faster also, right? So really reduce the amount of data that you need. In principle, this is what you want. But right now, I don't think it is. I think they should. Okay. Yes.
That was gonna be my question if you tried closing the loop, because you have this nice map, right, of all the deviations of which devices don't work.
Yes.
So have you chatted with them to say, recalibrate to make this error lower?
Yeah, but they're very reluctant.
Fair enough.
Great, I guess.
All right. Let's thank Dominik again for a great talk.